Uh, yeah, so I'm going to talk about profiling code in Rust, and my name is really Vitaly Bragilevsky, and I work at JetBrains, and we at JetBrains, we love Rust very much. And I will use Lion for doing this presentation. It's our main IDE for writing Rust code. But in fact, the things that I'm going to discuss here, they are a little bit more general than doing Rust with our Rust plugin in Lion. And Stefan said a very important thing, that he doesn't do profiling. And I would like to start with the results of some survey which was held like a year ago. But this survey is actually very, very disappointing. So we've asked, what profiling tools do you use for Rust? And it turned out that 84% don't use profiling tools at all. And this is very, very disappointing. And in this talk, I would like to discuss this situation. Why is it like that? So how can we do better? Do we really need that profiling? So this is what I'm going to discuss. It's actually a very simple talk. So I will give you several advices, but they're very simple and you can apply them and your code will be better and you don't have to work hard to do all that stuff. So, but profiling tools are not very popular among Rust developers. So let's discuss why. So maybe all those people, they just don't know what is profiling. So let's start with discussing definition. So if you look at Wikipedia, you will see a definition of profiling. So Wikipedia says that, and I will show you this definition part by part because every word there is very important. So we have to understand it clearly. So Wikipedia starts with this disclaimer. So we're going to discuss profiling in software engineering because, well, in real life, we have some other meaning of profiling, but in software engineering, it's a little bit special. First, profiling is a form of dynamic program analysis. You may know that there is static program analysis and dynamic program analysis. And static is done during compilation, and dynamic is what we do during runtime. So we run our program and we do some analysis. So we analyze some program behavior at runtime. So this is what is profiling. Then this dynamic analysis measures something. This is also important. So program analysis can do checks. For example, in Python, they have dynamic type checking. So they check types at runtime. So it's not measurement, but profiling measures. So we want to find out some characteristics of that runtime behavior. So what are we going to measure? For example, we measure space or memory usage, how much memory is used by our program. Then time complexity of a program. So how much time does it take to run that program? The usage of particular instructions. This is also important. How many times we read this and that. And finally, the frequency and duration of function calls. So this is what Wikipedia says. So we analyze runtime behavior of our programs in terms of memory usage, time, usage of instructions, and some characteristics of function calls. So this is profiling. Now, why we don't profile? And Stefan doesn't profile, and as he confessed, and all those survey participants don't profile. Why? All right. So why? We can think about several reasons, actually. So reason one, it's really hard. Or people say that it's hard. Maybe that's not the case. Maybe sometimes it's easy, but we don't know about that. And reason two is that it's not necessary at this time. So people say, well, we don't need to profile it right now because it's not a problem. So our programs are efficient enough. So it's just not necessary to do that now. And then they also say, so there are some very, very smart folks in our team. And in that team, so they'll do that when it's necessary. So like we have a team of 10 people and one of them is just doing profiling all the time. But if we postpone that profiling, then just imagine how many things should be fixed. If it's like we develop our program for a year and then we just start profiling. Isn't that a big problem? And then there is also another reason. Some people say that they don't want to do pre-match optimization. And you may know that this is a famous quote from Donald Knuth, that pre-match optimization is the root of all evil. So you may have heard about that. So here's Donald Knuth, and this is this quote. So pre-match optimization is the root of all evil. But as it is usually the case with some funny quotes, the real meaning of that quote is a little bit different. Because if we read it full quote, then we'll see that Donald Knuth doesn't ban pre-match optimization. So what he actually says, or he wrote in one of his papers. So he wrote that the real problem is that programmers have spent far too much time worrying about efficiency in the wrong places and at the wrong times. And then this pre-match optimization is the root of all evil. So pre-match doesn't mean that we do it too early. Pre-match means, in his quote, that we don't do profiling first. So it's not about banning profiling, banning like doing something to optimize our program. No. Donald Knuth suggests the real path. So first, we profile our programs, and second, we do optimization. And this is what we're going to discuss in this talk. So how to profile, how to find which places are right places to do optimization. So that's what we're going to do here. All right. To present some ways of profiling, I will use some small project. So I solved lead code problem number 22. I will describe it in a second. And using several methods. And then I just use this project as an example for doing profiling. So this problem is about generating well-formed parentheses combinations. Like we have opening parentheses, closing parentheses, and we put them together just to make it well-formed. So for example, if we have 3 pairs of parentheses, then here you can see the output. We have 5 possible well-formed combinations here. And in my project, I have 3 implementations. One is breadth first search, second one is depth first search, and sub-combinations. There is an information about that in the README file. If you look there, you can see what's going on. All right, so this is linked to the GitHub, and we'll explore this project right now, and we'll see what can we do about that. Okay, so if you are interested, here is the core code and link to this project. So let's see it. And remember, I'm in C-line, so I will use everything here. So to present this project. So first, let's look at the project structure. So of course, we have some source files here, and I have 3 implementations. They are all, I put them in separate modules. We have main file, we have library, so just as usual, library crate, binary crate, and all those implementations are in there. So we also have benchmarks here. We'll talk about them a little bit later. We have Dockerfile. I will show you why I need Dockerfile here. We have tests, of course, integration tests here. So this is our project structure. Quite usual Rust project, nothing special. We can run this project. So let me run it here. So first, I can run it using command line, for example, cargo run, and here is it. So I need to provide some arguments. There is some help. I can do that here. So a lot of information. So to run it, we need to provide the following. So I want, for example, to be verbose, and the size of the problem will be 12. Where is it? 12. And then I'm interested in breadth first search implementation. So like this. So if I run it, I will see some information. So if I don't want to write all those arguments, I also have some run configurations in the project. So I can run them like here, for example, run BFS. Here is it, breadth first search. So I don't need to provide arguments all the time. I just saved it in run configuration. Here is some results. And of course, I have tests, and I can run tests. So here is it. Everything is all right. So we're on the safe side. And whenever we change something, we can test again just to see that we don't break anything. All right. So this is small project overview. And now let's get to the main stuff. So what does it mean to profile memory usage? Here are several questions that we may be interested in. For example, how much memory is taken by some containers, some string or a vector or stuff like that? How much memory our program uses in total? So when and how we allocate memory, because memory allocation is some operation which requires working with the operating system. We have to do system calls. It takes a lot of time. So we want to know for sure when that memory is allocated. So is it deallocated correctly? Like people often say that we don't have memory leaks in Rust, and this is definitely not true. It's possible if you use reference counting, something like that, it's possible to get some problems. So there are several simple things then that we can do in this regard. So how we can profile that. So I'm going to present them. But remember, I'm not going to talk about something very sophisticated, not at all. So no sophisticated things, but we can do a lot using just very simple stuff. So let me show you some examples of the code, how we do stuff. So I will start with this. So let me just sort something. I will change some structure of my IDE here. So just to see everything, and I'll get back to presentation mode. So here we are. So our first tool is just asking for length and capacity of our data structures. For example, here you can see some information about memory usage in our program. So I just ask for the length of the vector, just as usual, and the capacity of the vector. So length is the number of elements in that vector, and capacity is the memory usage. So how much elements we can put into vector without changing its size. So very simple, but it's actually very helpful. So I think I can show how when we run it. So here you can see the size and capacity are just the same. All right, very simple. And we can do the same with strings, for example, string capacity. We can check that too. And so I computed here. So here is a problem with strings. And we know that if we have 12 parents, that means 12 pairs of parentheses. That means that the size of the string should be 24. But average capacity per string is 38. And that means that a lot of strings just use more memory that we actually need. So even if we look at such a simple characteristics, then we'll see that there are some problems, like 30% of memory isn't actually used for good. So a little bit of problem. Okay, then let's look here. So what is this function, dynamic usage? Usually vector doesn't have such a function. It comes from another crate. So I will show it here. It's from memuse. So if you add this dependency, you will get this function which tries to do its best to compute the overall memory usage of your data structure, such as vector or hash map. You can use this dynamic usage function with everything. So just add this library and you can get a lot of new information. And I also use human bytes here, just to present this information in this nice way. So you just see like 7.6 megabytes and stuff like that. Oh, by the way, it's a little bit outdated. I can update it right now. Maybe it's better. Yeah, hopefully nothing will break here. Maybe let's write check as usual. As we do that, we write tests all the time, and if it's fine, then okay, we are on the safe side. So just nice. Okay, so we can use very simple library to check memory usage, like this dynamic usage, and just we can get a lot of information about that. So how many memory is actually used by our programs. But these are very simple things. Let's use something more sophisticated. Namely, let's do real profiling. So I will use instruments. So I'm using macOS here. And in macOS, there is this program, Instruments, that actually shows you a lot of information about your program. So it's profiler for macOS operating system. So let me call it. So here I run a program with BFS and DFS one after another. And then I want to see how the memory is allocated. So I'm talking about memory allocation here. So let me run it. And it runs the program. It compiles all the information. And when it's over, it shows us how some information in a graphical way. Here is it. Here we are. So this is BFS, and you can see these steps, how memory is getting bigger and bigger. I'll make it a little bit like this allocation, then more allocations, even more allocations here. If we look at this graph, we can see, for example, that there is no memory leaks here, because this is our first BFS algorithm, and then almost every memory is freed, and then we start our second algorithm, and then again we do a lot of allocations, and then everything is freed again. So this behavior is actually very good. One possible problem that we can see from this graph is that we do a lot of allocations here. So we can see it's some stats here, but it doesn't matter for this moment. So when we do a lot of allocations, and you see these steps here, you can think about time which is spent on that allocation. So every time we ask operating system to give us more memory, maybe it's better to ask for that memory in advance. Then we'll ask it for just once, and then it will be this graph will be a little bit different. All right, so I will close it now. So very simple thing. In fact, if you are interested in this instruments library, you can use it with Cargo. There is a create Cargo instruments. You install it, and it's just some intermediate thing between instruments and your Cargo project. But of course, not everyone has macOS. Like in Windows, you have Visual Studio Profiler. Well, it's totally different, but the idea is the same. So you don't need to know a lot of things about your program to see this small graph. It's very easy. So many people have Linux, and in Linux, we have the main tool for doing profilings is Valgrind. So let's run Valgrind here. So I have special run configuration for Valgrind, and I use Docker to run it because, well, we have Valgrind for macOS, but it's not supported in a very good way. So let's run it in a Docker. So I have Docker container. I'll discuss it in a minute. Let me write run terminal here, and in terminal I go to the directory with this project. I do cargo build, and while it's updating crates, let's look at this Dockerfile. So Dockerfile is actually very simple. It's Ubuntu, and I install Valgrind, some Clang, C compiler, something very, very essential in order to make all this workable. And then I also install Rust, and I use stable Rust. And so very simple Docker container. And I use here Docker integration for Selenium, and it's installed. You don't need to install it because it's bundled with Selenium from the very beginning. So with this Docker file, we can run everything we want in a Docker container. So we have Valgrind and we have Rust, and then let's wait when this build is over. So my idea is to see that we can have the same graphs as in instruments, but for Linux. So we don't have to do something with our operating system. Sometimes profiling in different operating systems shows different results, but that's hard part. But we are talking here about easy parts. So for us, if it's okay in one operating system, then it's okay in another too. All right, so we've built it. So I can run it. So this is my path to the executable. It's target, Docker, it will be debug build. This is from program. So this is it. Yes, this is it. So I will write verbose version with size 12, and this will be BFS. So here is it. It just run it. And now I want to run it using valgrind. So it's just the same command line, but I add valgrind. And valgrind is actually a family of tools. And one tool I want to use here is called Massive. It's memory analyzer. In valgrind, there are several memory analyzers. So Massive is one of them. So I run it. And while we run it, it creates a file. We can see it here. And it's actually very, very long text file. But fortunately, there is a special program here to analyze it. It's called Massive Print. Okay. So once again, it's a lot of information, but there is something interesting in the very beginning. Let me show it to you. So here is it. This is actually the same sort of a graph we saw in instruments. It's in text form, but still it gives you almost the same information. The behavior can be a little bit different, like the behavior of allocation, because this part depends on the actual operating system. They have different allocators and different system calls and stuff like that, but still it just allocates something and then it's freed everything up. So this is the behavior of our program, and we can use it very easily, and we can see what's going on here. So in order to profile memory usage, yes, and we can see the amount of number of bytes allocated and stuff like that. So we can see these pictures, and if we change something, we can compare with those pictures and see if something is different. All right, now let's look at time profiling. Once again, very simple things. We want to know how much time does it take to compute results. And we also want to know where the program spent most time. And that means which functions are hot. So these two questions are actually the same thing. Hot means we spent a lot of time there. So how we can do that? The first very simple thing. We just use standard time functions from Rust. For example, here, I check time in the beginning, and then I run algorithm, and then I see how much time is elapsed. So that's it. Very simple. So let's run it. Run it again. So for example, this one. So it's just this information got result in this timing. So in many cases, that's enough. So I just mark the beginning, mark the end, and see how much time was elapsed at this algorithm. Sometimes it should be a little bit more interesting. For example, we can do benchmarking. And while doing benchmarking, let me show you my benchmarks. I use a criterion library here. So I will run it. Benchmarking, for example, this breadth first search. And what is actually going on here? Criterion runs our functions many times, like 100 of times. And then it computes some statistical characteristics. For example, here we can see this is average time we run it, and So this is for different sizes. Like if n equals to 5, then we have this 2 microseconds. And for n equals 2, we have 1 millisecond, and then 16 milliseconds for n equals to 12. So we can think about these stats. So we just benchmark them, and we can remember. And if we change something in our program, we can benchmark again and see what changed. So this is profiling time. So now we know that our functions take this amount of time for these sizes. We can also do profiling with a special tool here. So let me run profiler. So I use the same run configuration, but now, no, not that. But now I will ask for profiler. Here is it. And what we see here, it's so-called flame graph. And this flame graph is extremely important, and it's extremely important to understand what's going on. So this is all our program, like in time. And this is generate parentheses function. Like it takes 63% of the parent of this, most of our program. So most of the time is spent at this function. But if we look further, we'll see that the problem is that most of the time is used for reserve for push operation. And this is something that goes from vectors, Rust vectors. So why, instead of generating parentheses, instead of solving our problem, what we actually do is we reserve memory. And then we also do some reallocations. And then we allocate new memory. So most of the time, like 66%, is taken for vector operations. And this is definitely a very bad thing. So we don't want to spend time on memory allocation. And if you remember all those steps and now in our instruments graph or Valgrind graph, that's exactly because of this behavior. So we look there, we looked here, and we see that we have a problem in our software, in our code. So we've done profiling, and we see that a lot of time we spent on allocations, and this is not a very good thing. So we need to do something about that. Okay, what can we do about that? Several very simple techniques I want to share with you. Like, I'm sure everyone knows about them, but they're so simple. So sometimes we just don't do that. But they're not only simple, but they're also very powerful. So I'm not going to take your time writing code. So I will just show you what I already have. Actually, we are here, and I have several commits in another branch just to show you what's going on. So how to change that. And our first practice is to reserve memory in advance. So we use capacity for that. So instead of allocating memory when it's needed, we reserve it in advance, and then we reduce the number of allocations. For example, let's look here. Oops, not this one. I will need it here. Okay, let me again restructure these. No, sorry. I want to exit presentation mode to change a little bit this. Okay, here, this will be better. Right. So, fixing capacity. So before we had creating just new string, But in fact, we know the exact size of the string. Like if it's 12 pairs of parentheses, then we'll have 24 symbols, characters in our string. So we know the capacity. So instead of doing new, we say string with capacity, and we create string with exactly this capacity. So just reserving memory in advance. Very simple technique, but it's actually very powerful. And if we do that, there will be no excess memory usage inside strings. And we have a lot of strings, because you can imagine, like hundreds of thousands of them. Then we can do the same with vectors. Like here, I was creating just empty vector, and I push stuff to that. But it turns out that in our algorithm, I can compute the number, the future number of elements in that vector. And if I computed them, I can spend some time on computing. Doesn't matter what I'm actually doing, but I'm trying to predict the number of elements. And then once again, I use for vector this with capacity function. I create a vector of the specified capacity, and then I reduce number of allocations. So this is first very powerful but very simple technique. Then we can do resizing. Instead of resolving capacity, we can create new elements just in the very beginning. Those elements will be empty, and then using mutation, we can put the right values there. So for example, I'm doing in the next commit, like resize in advance. So how we can do that? Where are our changes? Like instead of having a vector, now I have a mutability reader, and instead of putting elements to the vector, I use that iterator to put things there. So I've created a large vector, and all the elements are already there. So I'm not pushing those elements. I have them already, but those elements are empty. So I just mutate their values. For example, here, the result element is combination, and I put new line. So I change line inside that combination. So I mutate that. Okay, and here I create new vector, and then I resize, and then I put these are my new elements. They will be empty, but the size will be correct. And then I'll change those elements. Here is it. My next technique is avoiding temporary structures. It's not always possible to avoid, because borrow checking can make it hard to do that. But still, when it's possible, it's a good idea to do that. So, for example, here, before I had a new vector, and now I just remove it. I don't have a new vector. Instead, I use the same vector and I resize it to be able to get all those new elements. So I go over first part of this vector, and I put elements in the second part of that vector. So in Rust, it's difficult to mutate several parts of vectors, like beginning and end. So it's not that easy. So here I use very nice function split at mute, which gives you two parts of vector, and both of them are mutable. So you can just do, so old part of the vector is first half, new part of the vector is second part, and you mutate something in the first part, and then you can mutate something in the second part, and during one loop. So very powerful, and you don't need a new vector anymore. And once again, you reduce number of allocations. So really, really very powerful. And one other technique here like it turns out that we don't need all those memory reservations at all, because we know exactly how much parentheses will be in this problem size, because it's so-called Catalan number and we can compute them. So if you have this function, doesn't matter what is it, but it gives us the size. So instead of pushing, instead of resizing, we just say, well, total capacity will be this one. And then there will be no allocations at all. And of course, whenever we do these changes, we have to check if everything is all right. So whenever we do all those optimization techniques, we have to test. So for now, let me check out this optimized version. Okay, here we are. And then, of course, I'll run tests. So this is optimized version. Okay. And now let me see what's going on in our instruments. So what's going on with our memory? Okay, we're on this program. Okay, and this is it. Okay, do you remember all those steps that we had before? And now there are almost no steps. Like, we reserve as much memory as possible. We've reduced allocation, and this program behavior is much, much better. So real difference. Okay, and if we, of course, we can also run our profiler. Okay, run VFS with profiler. And let's see. This is our generate parentheses function. And before we had a lot of memory reservation stuff here, and now we don't have it. We've just removed it. Okay, what about timing? Is it any better than before? Maybe it's not better. Let's try our benchmarks. Here is our benchmarks. We compile it again, we run benchmarks. And criteria library is so powerful, it shows us how much better our program, our implementation is. Okay, now it's improved 55% better. It's for smaller size and for another size also improved. And for the last time, I think it will be improved too. Yes. So everything is improved. So Criterion just is able to compare it with the previous runs. So you see that I showed you very simple things, very traditional Rust things. But if you do profiling at early stages, you just see all that stuff. And it's really, really very powerful. Well, of course, it's still hard. So I think I don't need all those windows. So we'll get back to my slides. So it's hard, but there are many tools, and I've showed you Valgrind family. I've showed you instruments. If you are interested, you can look at this library, DHAD-RS, which was designed specifically for Rust, and it allows you to introduce profiler into your program. You just add several lines, and then you have a lot of possibilities. It's also very, very powerful. So it's difficult to know all those tools, but it's a good idea to at least to get familiar with some of them. If you use Linux tools, they're mostly terminal-based. So you just run them and you see all those huge files. There are visualizers, you can look at them. But one important thing is that you don't have to understand everything in those files. Well, it's just not necessary. Instead, you just try to look at important parts. And that's enough for many cases. If you look at tutorials, then usually they focus on hard things. But it's not necessary to know all those hard things. In fact, in most cases, you don't need that. So I've showed you a couple of graphs, and then it's clearly visible that we have a problem. And then we've applied some simple techniques, and now it's clearly visible that we don't have that problem anymore. So you don't need to apply very sophisticated instruments, very sophisticated techniques to make your programs better. So that's important idea. As usual, for doing 80% things, you just need to master those instruments at 20%. No traditional Pareto rules. So it's hard, but you don't need all that. So I want you to start profiling as early as possible. Don't postpone it. Don't delegate it to other professionals because it's easy and it allows you to write better programs. And that's it for this talk. So you can download these slides. Here is the link, and feel free to talk to me in Twitter and whatever. And thank you very much.